Alright, so here's a few warm-ups for you to try before we get into our lesson for the day. Make sure you pause it and try them. Number 1 says write the general function for the following. General means we're not actually finding the constant of variation like we talked about in the other video. We're just writing what the form of the function looks like. So number 1 says x and y vary inversely. That means that the y values in this function are equal to some constant number divided by x. That is what inverse variation by definition means. So the y values are equal to some constant divided by x. We don't know what the constant is. That's why this is called the general function. We could also find the specific function if we actually knew a y value and an x value from that function. Number 2, area varies directly with the radius squared. So this goes back to that direct variation, which means some constant times the variable. So this would mean area equals a constant times the radius squared. We don't know what the constant is, although some of you might be able to guess that it's pi r squared if you realize that that's a area of a circle. But that is a constant number times the radius squared gives me the area. That's what direct variation means. So when you combine two variations, like in number 3, z varies directly with the square root of x and inversely with the cube of y, you would have z equals k times the square root of x over y cubed. In other words, z varies directly with the square root, so k times the square root, and inversely with the cube of y, so k over the y cubed. And that's combining the two variations together. So now, let's look at that example and let's find an actual specific equation for that one, so it kind of helps you with some of your homework maybe that you had. So if I had z varies directly with the square root of x and inversely with the cube of y, let's say that I know that z is equal to 10 when x is equal to 16 and y is equal to 2. Now I chose that x sort of wisely in this case, because I know that if I plug in 10 for z, I plug in 16 for x, and I plug in 2 for y, I will be able to solve this using techniques we've learned already this year. That looks kind of ugly, but it's really not, because the square root of 16 is 4. 2 cubed is 8. That means I have 4 over 8, or in other words, I have 1/2 k is equal to 10. So some of you can probably already figure out what k is, but if you multiply this side by 2 and this side by 2, it would tell me that it is 20 is k. So what would my specific function be? It would be z equals 20 times the square root of x over y cubed. So this general function is what the function looks like, the format, the form, if you will. The specific function is what you get when you actually have some values to plug in. If you don't have values, you can't get that constant of variation. Today's lesson is going to be relatively quick. There will be a few little pieces of it that are longer than others, but it's going to be a relatively short lesson because we are talking about graphing an inverse variation. And that sounds kind of scary when you first think about it. But really, it's very simple. In order to graph an inverse variation, the first thing you want to do is you want to make a table of values. Now, I'm going to make a really large table of values, but I'm also going to show you some shortcuts. First of all, when you make your table of values, here's your first shortcut. You are looking at an inverse variation, 6 divided by x. My constant is 6 in that case. And if I want to graph that, what are some numbers that I should plug in for x? I hope that you're screaming at the screen, numbers that divide easily into 6. Don't plug in random numbers into this. Plug in numbers that divide into 6. Also, thinking about plugging in even some negative numbers, even though it seems kind of weird, you can divide -1 into 6 really easily. So here's what I'm going to suggest. Always start with dividing it by itself. Divide it by 6. Then divide it by 3. Then divide it by 2. Then divide it by 1. Then I'm going to plug in 0, and then I'm going to plug in the negative versions of those. Now, I know some of you who are very smart may already be screaming at me about something, but hold on. What is 6 divided by 6? So if you plug it in, 6 divided by x, what is 6 divided by 6? 1. What is 6 divided by 3? 2. What is 6 divided by 2? 3. Notice those are flip-flopping because you know those are factors of 6. What's 6 divided by 1? 6. Also notice that 6, 1 and 1, 6 will always be true no matter what the constant is. You're going to have those two types of points. Now, obviously, it's not going to be 6 every time, but if it was 7 over x, it'd be 7, 1 and 1, 7. If it was 8 over x, it'd be 8, 1 and 1, 8. Those points are always going to be there. So there's another shortcut for you. You can automatically get those 2 points. And the negative versions of those. What's 6 divided by -1? -6. 6 divided by -6? -1. So those 4 points right there, let me highlight them. This one, this one, this one, and this one will always be on every inverse variation that you do. So you can use that as a shortcut. Just know that it's whatever the constant number is on the top. Also, like I said, the points in the middle should be fairly simple because those are going to be your factors. But also look down here. If you do 6 divided by -2, you get -3. 6 divided by -3, you get -2. Notice that that means that these points are also going to be just flipped over here. If they're flipped over the negatives like that, that should let you clue you in at least to knowing that there's going to be a mirror image, a reflection in this. Now, what about that 0, though? If I go and I take out my calculator and I do 6 divided by 0, it's going to tell me that that is an error, divided by 0, because that is undefined. We've talked about that when we talked about slope. That means that this doesn't actually have a point. And what that means is that causes a point of discontinuity on the graph. I'm going to write those words out because those are important, and you will see those later in your other math classes and maybe on a quiz or something for Mr. Harrison. A point of discontinuity. Basically, what it means is the graph is discontinuous at a point, because that means I'm going to physically have to pick up my pencil. This graph is going to make 2 parts. Let me show you what that looks like. So if I were to set up my 2 axes here, the point 6, 1 is going to be over here at 6, 1. The point 3, 2, 2, 3, 1, 6. Notice that kind of shape. It looks sort of familiar to exponential, but it's not, because the x is not in the exponent. But then you have -6, -1, -3, -2, -2, -3, and -1, -6. Notice the mirror image, the flip like I just talked about, because that's what happens when you divide those numbers. So there's your other shortcut that you can use. If you can get one side of this, you can get the other over here. But notice you can't plug in zeros. So that means there is not going to be anything on this axis right here. That actually creates what we call an asymptote. We have talked about that word before. The vertical asymptote is what this is actually called. Because a vertical asymptote is a point of discontinuity. It is a place on the graph that the graph does not touch. You cannot touch a vertical asymptote. Because essentially where it comes from, and I'm going to kind of oversimplify it here, but we're not going to get into the big ugly graphs of these. You should thank me. Basically what happens is it's a point because you can't plug in an x value of 0 on the bottom. You will not ever touch 0 for x. So it creates this vertical asymptote. Think about this as well. You have 6 divided by x. No matter how big the number you plug in for x, it's always going to be 6 divided by something. So it's never going to touch 0 for the y value either. So that creates a horizontal asymptote. A horizontal asymptote, same concept as a vertical asymptote. It is a line that this graph does not touch, but it gets closer and closer to it, just like it did with exponential equations. I will warn you that there are some ugly, weird guys in these rational functions that this chapter is about that do actually touch a horizontal asymptote. But an inverse variation will not, because it always has just a number sitting there on the top. So basically what this graph looks like is kind of these two little ramp shapes that are in the corner that never touch the asymptotes. You could put in your own joke right there if you would like. Don't touch the asymptotes. So, sorry, math teacher joke. So those two branches or two pieces of that graph is a characteristic of rational functions. We're not going to get into huge detail about the way these graphs look in the uglier rational functions, but I'll just mention it briefly as we go through the rest of this. So, this is what every inverse variation function is going to look like. The only difference is the numbers that you plot for your points are going to be different depending on the number on the top. So, if it was 16 over x, notice that my points for my table of values could include things like 16 and 8 and 4 and 2 and 1 and then -1 and -2, -4, -8, -16. I could have a bunch of points, but some of these are going to be really quick because 16 divided by 1 is going to be 16. 16 divided by 16 is going to be 1, and then there's going to be the negative versions of those. Again, 4 points always, really quickly. 16 divided by 8 is 2. 16 divided by 2 is 8. And then the negative versions of those. 16 divided by 4 is 4. 16 divided by -4 is -4. So you get those right there. And that one, by the way, is another little special point. If it's a perfect square on the top, you're always going to have that perfect square 4 times 4 in the middle. Or -4 times -4 is 16. And then this graph would follow the same kind of pattern that the other one did. We would go through. Wow, I need to change that to black axis here. Come on, why is this thing not working? It's not liking me. So, we have 16(1) would be way out here. 116 would be way up here. Same thing, we'd have the negative version of that. And then we'd have the negative version of that. Mirror images, remember? Then you would have 2 and then 8. 8 and then 2. 4, 4. And again, that one right there, notice that little square root, 4 and 4, is always going to be the closest one to the axis. And that will be true, to the origin, excuse me. And that will be true even for ones that are not perfect squares. Even if you looked at 6, the square root of 6 is going to be about right there, about 2 point something. So it's going to be really close right there in the middle every single time as the square root. Just nice if it's a perfect square like 16. You're always going to have those asymptotes because you can't plug in 0 for x. You're going to have a vertical asymptote at 0. You can't plug in 0 or get 0 for y ever, so you're going to have a horizontal asymptote. And then it's going to have these branches of these graphs that have these characteristic shapes, kind of like a ramp, sort of. And yes, Mr. Harrison kind of got a little shaky there, sorry. Been a little while since I've been graphing, because we hadn't graphed a whole lot since we've been home. But that's what these look like. Notice that it's in quadrant 1 and quadrant 3. So the graph is not linear, obviously. The graph has 2 parts or branches. The x-axis is a horizontal asymptote. The y-axis is a vertical asymptote. And the domain is any number except one that makes the bottom of the fraction 0. We can't plug in 0 on the bottom because that is undefined. So it creates these branches in these quadrants 1 and quadrants 3. Well, what would happen if I switched that to be a negative 16 instead of a positive 16? To save a little bit of time, I'm going to go to my y equals screen here. I'm going to turn off the plot there. And I'm going to do negative 16. Negative 16 divided by x instead of positive 16. And graph that. And let's go to Zoom Standard. Notice what that does is that flips it to quadrant 2 and quadrant 4. But it still has the same characteristic shape. So if you see a negative 16 here, it would just flip it up here and down here, and that would still have the same asymptotes. So for 16 over x or 6 over x, always going to be in quadrant 1 and quadrant 3. If you change those to negative 16 over x or negative 6 over x, it's always going to be in quadrants 2 and quadrants 4. But, again, shortcuts there. Think about 16.1 and 116, and the negative versions of those are always going to be there, so you can always find those 4, I'll say corner points, so to speak. Then you use factors for the rest of them. You're always going to have your vertical asymptote and your horizontal asymptote. Now, what happens, just like other graphs that we've done this year, what happens when you have something that looks like this guy? And I'm going to use these letters because I think your textbook does. If they don't, it's okay. It's not a big deal. Letters aren't the important part here. Let's say it's k over x minus b, and then you have plus c here. So, Kendall, son. My son's coming running in here. He's bottle flipping, so he's getting real excited. He made shots. Sorry about that. So, you have your constant over your x, but now you have a minus number or plus number here, and a minus number or plus number here. So what I mean by that would be something that looks like this. I'm going to give you an example here. Y equals 4 over x minus 2 plus 3. So think about all year long when we've had this minus and plus number beside the x and out on the end of the function. All year long we've talked about how that translates the function. How this guy right here moves it left and right. This guy right here moves it up and down. And we've said all year long that you take the opposite of this one and the same as this one. All year we've done this. This is not new. This is the second chapter of the year. The only time we didn't do it is the first chapter. So you have 4 over x minus 2 and then plus 3. If I want to graph this, all I have to do is focus in, not on the whole thing, but just on the 4 over x, what that looks like on a graph, just like we did just a few minutes ago. And then move it right 2 and up 3. So I treat this the same way with that whole parent function technique, and then move it. And what it's going to do, though, is it is going to move the vertical asymptote over that many spaces to the right, and going to move the horizontal asymptote that many spaces up as well. So let's do this one in particular. So let's say we have y equals, like I said, 4 over x minus 2 plus 3. I'm going to go and I'm going to make a table of values just like I did earlier. Here's the difference. I'm not going to do the whole thing. I'm just going to do 4 over x, the parent function we call it, guys. Don't do everything, because this minus 2 and the plus 3 is just going to be ugly and ridiculous trying to plug in a table. So go to something simple here. You know you're going to have 4, 1 and 1, 4. You should also know that you're going to have the negative versions of those. That's what I told you, those quick little shortcuts you can use. You also hopefully should know that the square root of 4 is 2, so you're going to have 2 and 2. 2 times 2 is 4. Or 4 divided by 2 is 2. And you're going to have the negative version of that one. And so you already have now this graph right here should go through and be those points that are in quadrant number 1 and quadrant number 3. And I'm going to just plot light versions of those real quickly. Don't plot these on your own if you don't want to. 1, 4, 2, 2, 4, 1. And then the negative versions of those. That's where it is right now without the translations, without the transformations. So we take it and we move it right 2 and up 3 now. But watch what happens when you do that. If you move this one right 2 and up 3, you move this one right 2 and up 3. You move this one right 2 and up 3. Right 2 and up 3. Right 2 and then up 3. Right 2 and then up 3. You're going to notice it's, Mr. Harrison, you said we couldn't touch the asymptotes. You're right, and it's kind of funny when you say that, but remember, if it moves those, it also moves the asymptotes. So what it does is it moves the entire graph, everything, including the fact that there's going to be still a horizontal asymptote here, up 3 at positive 3. There's going to be a vertical asymptote here at positive 2 because it moved to the right 2. It moved that asymptote to the right 2 spaces. And then it's going to be the same little curves that we expected, just like the other ones. Now, I have some people who say, Mr. Harrison, can I just move the asymptotes and then graph my curves? Sure. If you like to move your asymptotes, move your asymptotes. Sorry, another math teacher joke there. Anyways, what I'm saying is you can move the asymptotes right 2 and up 3 and then draw your points. That's fine. Either way, it's taking this entire graph and moving it right 2 and up 3. And guys, here's the reason the asymptote moves also. Just think about this. With this minus 2 on the bottom here, the reason we move the asymptote right 2 is because you cannot plug in 2 on the bottom. 2 minus 2 would be 0. Divided by 0, you can't divide by 0. The plus 3 makes this whole graph move up closer to 3 because this plus 3 is always going to be getting closer and closer and closer and closer. 4 divided by 10,000 plus 3 would always be just barely above 3 way out here. So it doesn't matter. You're always going to be getting closer and closer to 3 right there. So that's how you graph a translation. All right. So that's really the big key with this section. I do have one more thing I want to show you. Okay. One more example, and I'm going to use a couple examples from your book. So I'm going to grab those real quick before I do. And this kind of goes back and just practice the little thing of division that we did in a previous polynomials chapter. So that's why I wanted to kind of throw it in here, but also show you how it ties with what we're looking at here. A rational function. Wow, I can't write right now. Let's try that again. A rational function is a function that can be written as a ratio, or a function that essentially is one polynomial divided by another polynomial. But they can get really ugly. They can get a lot uglier than this. Okay, you can get into some quadratics on the top or on the bottom. You get into cubics on the top or the bottom. But it's polynomials on the top and polynomials on the bottom. So it is things that you've worked with before. They're not random new functions on the top and bottom. But because there's two of them and they're dividing, that's why it's called a rational function, a ratio. What that causes is that causes sometimes some really crazy stuff that can happen on graphs. But if you have right here the degrees that are the same like this on the top and on the bottom, this is x to the first and this is x to the first, you can actually use division. You can do that old long division technique where we fill in the spots here of our standard form, x to the first, and then no x right here, x to the 0. And then we divide it by x minus 3. Remember, you divide the first one on the inside, divided by the first one on the outside. 4x divided by x is 4. If you do 4 times x, you get 4x. 4 times negative 3 is negative 12. If you subtract those, remember you have to distribute the negative, so it makes this one negative, makes this one positive. That cancels this one out. 0 plus 12 is 12. That's my remainder. Now, when we were doing long division, one of the things I told you is that if you divide those, 4x divided by x minus 3, you get 4, and then plus the remainder over the dividend, the divisor, excuse me, the thing that you're dividing by on the outside of the house. But look at this right here. This is what we just did. 12 over x minus 3, and then that plus 4. That means that this right here is going to be that transformation, just like we just talked. So this particular function, 4x over x minus 3, it's kind of ugly looking, right? Wouldn't know how to graph it if it looked like this, maybe. But now I can if I divide it here. And so what that gives me is oh, then my horizontal asymptote is going to be up here at 4 because it moves up 4 spaces. I'm going to have a vertical asymptote right 3 because it's going to move right 3. And then I'm going to have that characteristic curve here and characteristic curve here. Now I know I'm just kind of sketching that, but that's how I know what that one's going to look like. Now, when you get into pre-cal, you're going to talk about how there's another way to go through and figure out where the asymptotes are, even if you don't want to actually divide it, which is a good thing. I'm not going to teach you that in this class because I'm not going to focus on those graphs. But essentially what you're looking at is when you have an ugly function like this, 4x over x minus 3, or even if it got even uglier, let's say h of x equals x plus 2 times x minus 4 over x squared plus 3x minus 9, something like this. Or let's go minus 28, something like that. What you have there is you have things that you can factor, just like we did way back in the day. See the factors on the top of this one? And then on the bottom of this one, you have factors, x and x, plus and minus, because it's a negative 28, 7, and 4 will give me that. This would cancel out, and that would simplify the function. We are going to talk about that later, but that would also cause what's called a hole in the middle of the graph. The x plus 7 on the bottom means I can't plug in negative 7 on the bottom because that would be 0 on the bottom. There would be a vertical asymptote at negative 7. The degrees being the same on the top and on the bottom would make it division. 1 divided by 1 means there'd be a horizontal asymptote at 1. And so I go through all these little pieces. Instead of having to actually divide it like I did this guy and get it to look like this, there's other ways to find out where those asymptotes are and which way it curves. But you're also going to have some crazy looking graphs for this sometimes, where you may have a vertical asymptote here and a vertical asymptote here, a horizontal asymptote here, and you may have these weird looking curves this way. Wow, Mr. Harrison. Over here, curves like this. You may have all kinds of little funky looking curves because of all the things that can happen in craziness in there. We're not going to worry about that. All I want you to be able to do for your homework is do a simple little quick long division and make it look like the transformations that we talked about. Okie dokie. So that's basically your lesson for today. That is all the stuff with graphing a function like that. Now, as a final little note, some of you may be thinking, okay, so yeah, that's a ridiculously ugly function. When do people use those? Sales is a big one when you have a percentage or proportion, when you have a ratio like that. when you have one function compared to another function. It's that's usually when you see these types of rational functions where you have the sales of one item compared to another sales of another item, and you want to find the rate or the ratio that one is selling compared to another. You get into some big ugly functions like this. So anyways, go back through, watch this video a couple times. If you need some extra help on WebEx, please let me know. I love you guys. I miss you.